Good morning, everybody. We are Senior Design Group 15. The project that we chose is the United Launch Lines Emergency Egress System Cable Inspection Tool. My name is Jason Wessner. I'm an electrical engineering student. We had Zach Gilliland, he was a computer engineering student, and then Bryan Core, he was electrical and computer engineering student. This was an interdisciplinary project, so for our chassis design, the mechanical team was Shane Grayford and Nelson Rodriguez. And then for the data processing, we had computer science team was Stephen Faber and Joseph Potter. Here's a brief overview of the presentation that we're going to give you today. You can see the picture on the right shows the tower at pad 41. Anytime that you have space flight with humans on it going off, we need to have an egress system for them to get out of the way of danger prior to flight. And this is not only for astronauts, but also for the technicians that are up there with them. So here you can see you have 4 cables that take you away, and they get up to, with the people on them, they get up to about 55 miles an hour getting you to safety, and it's about 1,300 feet away when you reach the bottom. So why is this here? It's there for personal safety. That's our key goal here. And you can see from the picture, you can see those four lines going into the top of the tower, and then you can see on the left there, that white thing that's sticking up, that's actually the crew access arm. That's where they get on the rocket. So you can see it's at the same level. Something happens, they can get to there very quickly and get to safety. Now, rocket launching is not a guaranteed success. We've seen in the past, people get complacent, things go wrong, stuff that's not expected. So what we need to do, we need to be ready for that, something that may happen, and have a backup in place to hopefully get people to safety. And that's where our team comes in. We have these 4 cables there that are there for the backup purpose of getting people to a safe place. And we need to make sure those cables are ready to support at any time. It would be an extreme tragedy if something happened, they get on these cables, and then one of the cables failed and somebody got hurt due to the egress system instead of from the rocket itself, whatever went wrong. So these things are out in a harsh environment. If you've ever seen a picture of the launch pads there, they're only about 200 feet from the water. You got this constant salt air. We're in Florida, so we have a lot of lightning strikes. We have rocket launching going on literally right next to this tower. So you have the Atlas uses solid rocket motors, and the debris that comes off of the solid rocket motors is actually extremely corrosive. So, and we also have hurricanes. So you have all these things that combine to a very bad environment for these cables. So currently they're manually inspected after every major event. And like I said, it's over a mile of cable between the 4 of them. They're each 1,340 feet long. So the process is very long. It's a major ordeal to do it. And it's up to 200 feet in the air at the top. So it's also a hazard for workers to be out there working in that space. So the objective for our project was to create this automated inspection tool. So we wanted to be able to put this thing on the cable and basically hit start and it do its job. Now, it needs to be able to be powered to move under its own power. So it's going to be going up the cable, sensing when it gets to the top, and then returning to the bottom. So it has to be a very smart device in order to keep up. So as it's going along, we wanted to collect data. So the first thing that we're looking for is that visual inspection that they do after the events. So we decided to go with 4 cameras mounted around the cable, and as this thing's moving, it's going to be capturing images every couple inches, and each one of those images that it takes is going to be a longer distance than what they had traveled, so you'll get overlap in your pictures, which was required from computer science. And then all these pictures will be put together by the computer science team, and they'll make this 3D model, which is what ULA wants from the cable. So along with these pictures that we're going to be utilizing, we're going to be able to look at the diameter of the cable. So this thing is very heavy. It's extremely long. So it's got a lot of tension on this cable. So over time, if this cable begins to weaken, it's going to stretch, and the diameter is going to shrink as it stretches. So that can be like a red flag for the ULA folks. So that's why they want us looking at the diameter of the cable. So that's also going to be incorporated in the design. It needs to be able to hold up to the same environment the cables are in. So we need corrosion-resistant materials for this thing to be built. We have a 4-hour window to complete our process. So that was one of our biggest challenges, was to be able to try and meet this 4-hour window. Now for that, you can see from our requirements that we have to be able to move at least half a foot per second just to keep up with that to make it in 4 hours. We have over a mile of travel to do, so we have a very far distance to go. The inspection tool, like I said, needs to be able to know when it reaches the top. It needs to have the ability to reverse directions if needed. We need to be able to control the descent. The device itself should not be capable of coming off the line and falling up to 200 feet to the ground and hurting somebody. So we have to have some backups in on the chassis itself to make sure that can't happen. Okay, so the inspection tool needs to be able to run the entire 4-hour window on a single battery. ULA does not want any components changed during inspections. So there's 4 different cables. They didn't want us changing out parts between each cable. Another requirement was the size of this thing. We know it's going to be put up, the cable at the bottom is about 12 feet off the ground. So people are going to have to either get up on a platform or a ladder to install it. So we didn't want it to be more than one person can handle. So it has to be less than 45 pounds by OSHA. And we also want it to be less than a cubic meter in size due to the fact that it's going to be moved around a lot. So last year there was 3 senior design teams from mechanical only that did this similar process, and you can see the picture on the left is one of their designs, and you can see it's very bulky. It was very heavy design. It was like 50 pounds. It was bigger than what we liked. And so on the picture on the right, this is actually a high voltage inspection line, and they do a little different process. They're using EMF for their inspection of the inside of the cable, but we just like the overall chassis and the sleek look of it, so we kind of just based ours off of that a little bit. Here's a quick overview of what the outside of it's going to look like. The tubing on the top there, you can see it's aluminum and it's hollow. So all these joints are welded together, so it's very strong, very lightweight, much better design than what the previous teams had. The size of this thing is about 24 inches by 14 by 14. It's a little bigger than what we started with, but in order to get all of our sensors in there, we had to make it a little bigger. Here's with the door shut, what it's going to look like. You can see the 2 notches where the cable will slide up. Here you can see the door open. You got your cameras mounted on the door there, and then on the bottom just kind of gives you a visualization. Here's a picture from the end kind of looking in. That's the clamping mechanism that they came up with. You can see the U-shaped wheels that they have. That creates more traction for the motor. You can see on the white there on the right side. And it also surrounds the cable so it can't come off. Here's a picture with it in place. So it wraps around that cable very tightly to keep it from coming off and keeps the tension on there so that the motor can do its job. See the 4 cameras that are mounted around the cable there that will be taking the pictures. And here's just the outside view of what it's going to look like when it's actually enclosed. So here's for the electrical system. We get into our stuff. So we had the microcontroller. This is going to be controlling all the sensors going out. We got the encoder for the distance, and we're going to have diameter sensors. We're going to have a pulse width modulation signal that goes to the motor driver. That's going to control how fast we're moving. We're going to have the motor itself that actually moves the device, and then we have the battery supplying power to everything. And down below we have a separate camera controller, so we're going to have 4 cameras taking pictures simultaneously, so we're going to feed the data to that and to store it, so instead of trying to run it through the PCB. So here's how we broke it apart. You can see our subsystems. Now, if you look at the legend at the bottom, the colors can be associated with which person took on the task. And then if you look at the task itself, underneath each one is the backup to that person. And then the ones that are in gray on here, you have the chassis was the mechanical team, and the data processing was the computer science team. So our drive motor for this thing, we went with a stepper motor. We wanted a little bit of precision when we were controlling it. So when we did our analysis, this cable sits at about 8-degree incline, so we came up with about 1 Newton meter of torque, a little bit less that would be required. So this motor that we chose is actually a 1.16 Newton meter NEMA 23 stepper motor, so that means the front of it's about 2.5 inches by 2.5 inches, and for this particular model, it's about 2.5 inches long, so it's very light, compact. It only weighs like a pound. It's very lightweight. It's about 1.5 amp current draw. So it's going to be this constant draw, but our battery can definitely hold up to that amount. So it's a perfect fit for our selection. For the control of this, we went with a motor driver. So when we were looking at stepper motors, due to that constant current draw that they have, they tend to try and draw more current and overheat. So this is our protection device that we have on it, is this driver. So one thing that's really cool about this driver, it really eliminated a lot of headaches for us in the design. So instead of trying to design something that can handle that 1.5 amps of current coming from that needs to go to the motor, the battery connects directly to this driver. We'll supply a pulse width modulation from our microcontroller to this driver, and we don't have to try and support that. Everything goes through this driver. So the battery goes to the driver and out to the motor depending on our pulse width modulation. So one of the other things that's nice, we have a single input pin on this device on the driver itself that, depending if it's a 1 or a 0, the direction changes of the motor, and then we have an enable pin where we can turn it off, which is nice. This driver itself was rated from 1 amp to 3.2 amps, and it's rated for NEMA 1723, and then it's 10 to 30 volts, so it's right in the size that we needed. So we looked at comparing the different motors that we could use on our inspection tool. So we looked at originally at a DC traditional motor, and then we looked at stepper and servo later, and they all had high torque. The problem with the DC, you didn't have any accuracy or control over the motor really. So as the incline changes, it kind of sags in the middle, so you get a different incline. So we didn't want the speed changing, because then when our pictures are captured or the images are taking, they're going to be at different spots. So we wanted to make sure to have this constant motor speed so that we could make sure that our pictures were taken at the same time. For the stepper motor, the price was the biggest thing why we didn't go with servo. Servo motors are high, and we really didn't need that much precision. If we were within an inch, that was plenty, and we have enough precision with the stepper for what our project needed. So below the second table here, you can see there's a couple different sizes. There 1.16 was one we went with. That was the cheapest option, and then as the torque went up, the price went up also. The second one was from a different company. They're a little bit higher on price. We didn't need any more torque, so we just went with the cheapest option we found. So as we were looking at our design, we were going to be trying to figure out how to disengage the motor for free fall, and we decided to go a different route and actually use the motor during free fall to generate power. We're going to be falling for 1,340 feet back to the bottom, so why not generate some power on the way down? That's all a generator is. It's just a motor being forced to turn. So we're going to utilize that in our design. Another thing that came out of that was we can actually use it for our braking. We want to slow it down. We don't want it going too fast. So this is actually going to create a little bit of resistance on there and slow us down a little bit and then help us brake. So when we started doing our testing, you see we hooked it up to a drill, and for each of the motor coils, there's 2 different coils on this motor. For each of the coils coming out, we got a perfect sine wave, which was really cool, and they were just a little bit out of phase from each other. So we can put those through some rectifiers and connect them to a capacitor in there, and then we'll flatten it out to a nice DC signal that we want coming out to help us charge the motor and make the battery last a little bit longer for our inspection. For our braking, we can put either a resistor or just simply short the cables of that the motor together, and that'll create resistance back on the motor and slow us down. So during the testing, we used the drill to run this motor, and then we used it in 2 different speeds, low speed on the drill and then high speed, and we could see that as the drill was spinning faster, you'd actually get more output as expected from this. So we're probably not going to be spinning as fast as the high speed, but it was just more of a proof of concept of what we expected to see out of it, and then we used different size resistors in line.
Here's the schematic for our PCB. It consists of the MCU and the motion and braking circuits, as well as its interface to the sensors and the Raspberry Pi. The Raspberry Pi connects through a 40-pin ribbon connector, which communicates back and forth to the MCU through voltage dividers and logic level boosters, since the Raspberry Pi is a 3.3 volt system and the MCU is a 5 volt system. The various sensors, like the ultrasonic sensors and the encoder, connect via pin headers and terminals. The MCU drives the relays on the right side of the board through NPN drivers, which allow it to control what the motor is connected to. The connection options are normal drive operation, regenerative braking, and full stop braking. In normal drive operation, the relays connect the motor leads directly to the motor driver. In regenerative braking mode, the motor leads are connected to full bridge rectifiers, which are followed by very large capacitors that feed into the battery. In full stop braking mode, a dedicated external line is connected to the motor leads, feeding it constant maximum current to give it the maximum amount of braking. Here's what the physical PCB looks like. It's a 2-layer board, the top layer being shown in red and the bottom in green. The vendor we chose is Express PCB because we've had previous experience with them, and they're also a US-based manufacturer. ULA is not able to order parts from foreign countries, which greatly limited our options for PCB manufacturers. We opted for a controllable lighting source inside the inspection tool. Having consistent lighting is important for a reliable operation of the CS team's software processing. The product we chose is a 9.8-foot LED lighting strip which can be cut to any desired length. We cut the strip to 4 feet to suit our needs and calculated that this length would require approximately 1 amp to drive. We compared various lighting technologies and determined that LEDs were the best option when compared to the high power usage and lack of controllability of incandescent and fluorescent lighting. The particular model of LED strip chosen is shown. The LED strip has an optional attached dimmer knob, which will be set for optimal brightness and then left alone afterward. The LED strips will also be covered with a diffuser strip, which will help even out the spread of the lighting.
The primary data collected by the inspection device is image data around the circumference of a cable. To accomplish this, we use 4 UVC-compliant USB camera modules. 2 megapixels was found to be high enough a resolution for the computer scientist's computer vision module, so we selected the high frame rate spinal 2 megapixel solution. The exposure time left a little to be desired, but this camera's small form factor and low cost made the option stand out. Modifications to the inspection device's control were made to accommodate for the exposure. We also discovered that it's difficult to find high frame rate cameras as small as we required, and also with minimum focus distances as close as we needed.
The device must be able to accurately track its position along the zip line. For this sensor, we chose to use an incremental rotary encoder. The particular model chosen has a very high resolution of 1024 pulses per revolution. When combined with the included 200 mm circumference measurement wheel, this provides a resolution of just 0.195 mm per pulse. Other potential options considered for tracking position were an absolute rotary encoder and simply counting the stepper motor pulses. However, an absolute rotary encoder has a limit on the maximum distance it can turn, which is problematic for the very long lengths of the zip lines. Counting stepper motor pulses is also risky, as it runs on the assumption that the motor won't slip or miss steps. The device must be able to sense proximity to the ends of the zip line, as well as measure the diameter of the cable at any given point. For both these purposes, we chose to use the very common HC SR04 ultrasonic sensors. The sensor has a range of 2 centimeters to 3 meters with an accuracy of plus or minus 3 millimeters. The cable diameter data is collected by the MCU and forwarded to the Raspberry Pi over UART. Another option for this purpose was a laser-based sensor, but these systems are more difficult to set up and are cost prohibitive despite being more accurate. The ultrasonic sensor was deemed sufficient for this purpose. 2 main control units were utilized for this project. The first is a microcontroller chip, which handles the real-time drive and measurement devices like the stepper motor and ultrasonic sensors. The second control unit is a Raspberry Pi, which handles the slower, more intensive processes like image capture and data storage. We decided to use an Atmel-based MCU due to the larger abundance of community resources compared to competitors. For the chip itself, we chose the ATtiny 2313 because it had exactly the right number of timers needed and integrated hardware UART in the smallest possible package for the amount of I/O we required. We chose to use a Raspberry Pi because it supports easy operation of the cameras over USB, and it has programmable GPIO lines which can be used to communicate with the MCU. It can also be loaded with a lightweight headless Linux operating system, saving on system resources. Saving and transferring multiple gigabytes of image data is very easy thanks to the SD card slot and USB and Ethernet ports. Finally, it is an easily replaceable COTS device, which is a bonus for ULA. The device must have sufficient storage to contain all of the image data from all 4 cables. Each image taken by a single camera results in a roughly 900 kilobyte JPEG file. With 4 cameras and images being captured every 3 inches, each zipline will result in approximately 20 gigabytes of images. Thus, a 128 gigabyte micro SD card will be sufficient. Different storage technologies were examined for this purpose. A solid-state drive offers the highest speeds and capacities, but is also the most expensive and least portable. A USB stick offers slower speeds and lower capacities at a lower price, but would be difficult to integrate into the design for convenient removal. We settled on a micro SD card, which offers similar capacities and speeds to a USB stick, but in a much more portable form factor. The speed of the storage was not determined to be a significant factor during analysis.
To ease in the operation of the device, a user interface has been designed with a focus on simplicity. The power switch is the master cutoff for all systems on the device. An LCD screen displays which cable is selected, along with various notifications such as storage overwrite warnings. In operation, the device can be thought of as having 3 stages. Upon flipping the switch, the Raspberry Pi takes about 15 seconds to boot. The operator is then able to select which cable to image. If no previous data exists in storage, the Pi will signal the MCU to begin. In the data collection stage, or the ascent stage, the device steps up the EES, taking 4 images and 2 diameter measurements every 3 inches. The MCU pulls its proximity sensor and continues on its way. Once the MCU senses the top of the EES or any large object in its path, the motor disengages to begin freefall. The MCU waits for the encoder to spin back down, and when the encoder shows a slowing in descent or reaches a braking zone, the motor will re-engage and step down until the back-facing proximity sensor finds the base of the cable.
The device should be able to operate continuously under its own power for the entire time required to inspect all 4 cables. For convenience reasons, the battery should not be swapped in between each cable inspection. The battery should provide a 12-volt nominal output with at least 6 amps of continuous current. It should also be rechargeable for environmental considerations. To determine the capacity, we compiled a table of estimated current draw for each subsystem. Over the course of 4 hours, we estimated a minimum capacity of 23.3 amp hours. The battery size chosen was 30 amp hours. Different battery chemistries were considered for this purpose. A lead-acid battery would be far too large and heavy to be practical for this purpose. Nickel-cadmium batteries are lighter and still cheap, but are still quite heavy and suffer from memory issues. Lithium-ion batteries are the smallest and lightest, but tend to be more volatile and less resilient to harsh conditions. Lithium iron phosphate was chosen because it is still very compact and lightweight, but is much more stable and long-lasting.
Here's a quick overview of the CS team's computer vision algorithm and in-user application. The data is transferred to their device running an OpenCV program that flags anomalies and keeps a tally of the positions of the problem images. The images are wrapped around 3D cable models using ColeMap, and finally the results are presented to a user on a web-based GUI. The OpenCV program looks for discoloration, such as that caused by lightning strikes, as well as edge detection outliers, such as frayed or broken strands. Here's the CS team's rough design of the GUI, showing past inspection databases, the model of the cable, any flags present in the area, and raw image data. These are the order form parts lists over the course of this project. In total, all 3 teams spent about $1,925. We want to express our gratitude one more time to United Launch Alliance, the sponsor of this project. They provided extensive funding and has allowed us excellent access to their facilities. We also want to thank the University of Central Florida and the College of Engineering and Computer Sciences Department of Electrical and Computer Engineering.